Hello, happy Friday. So we're going to get started with today's lecture recap, and I'm going to quickly review what we talked about last time, and then we'll get on to our main subject today, which is basically going to be applications of the various thermodynamic formulas that we've kind of understood up to this point. And so last time we were talking about the various contributions in the first law of thermodynamics, which was basically our energy conservation equation. It said that if you add heat to a system, and then that system also does some work, then the total change in energy of that system is the amount of heat that you've added minus the work, which is the amount of energy that your system transfers to its environment through mechanical means, through expansion of the gas, for example. And then at the end of last class, we were talking about, or in the middle of last class, we were talking about what does it mean, this change in energy of the gas? How do I relate that to other quantities that I can measure? And so we understood that the meaning of it, the meaning of the energy U, is basically just the sum of all the energies of the molecules. So that can include kinetic energy and rotational energy, vibrational energy of molecules, and potential energy if it's not an ideal gas. And the way that we detect these changes in energy of the gas is just by measuring the temperature. And so the change in energy U is directly related to the change in temperature. It's proportional. And we have our main equation, delta U equals the number of moles times the molar specific heat times the change in temperature. Okay. And so in the context of thermodynamic processes, we can predict the change in temperature by looking at how much heat goes in, how much of that energy is then taken away by work, and then the remaining energy tells us the delta U, which then we can use to predict the change in temperature. Okay. So now just to kind of summarize then all of the things that we have to analyze various processes, kind of listed them here. And so the kind of thing that we'll be interested in doing is analyzing things like cycles in an internal combustion engine or other kinds of heat engines or refrigerators. And often there'll be some kind of cyclic process. So these engines basically do the same thing over and over and over again. And the basic idea is that they take one form of energy, which is usually heat that we're adding to the system, and convert it to other forms of energy. And so the thing that an engine does is it produces a net amount of work in a cyclic process. It converts some of the heat that you put into the engine into this work. And the kinds of things that we'll be interested in are understanding how much work is produced per cycle of an engine, how much heat do we have to add. There's some efficiency factor, which is how much work that we get out of each cycle divided by how much heat we have to add in. That we'll learn is something generally less than 1. And so we'll be interested in calculating that for different kinds of engines or different kinds of cycles. Similarly, we can look at refrigerators, where in that case, we're actually doing work, and the goal is to remove energy from some cold system so that you can keep it cold. Right, so the specific kinds of things we'll be doing will have a particular process, and it's often useful to display that process as some cycle on a PV diagram, just keeping track of the various pressures and volumes during the process. And often these cycles can be approximated by certain special types of processes, such as a constant volume process, as you see here, constant pressure processes, constant temperature processes, or sometimes what we call adiabatic processes, where the heat going in and out is equal to 0. And so to analyze these systems, then one kind of thing that we'll want to do is say understand the temperature and the pressure and the volume at all the different points on the cycle. In order to do that, we'll often be using the ideal gas law, which relates the pressure, volume, and temperature. The number of moles is typically going to be remaining fixed. next thing we'll want to do would be to calculate the work for various parts of the cycle, or for the net work for the entire cycle. We've understood that we can use P delta V as a calculation of work when the pressure remains constant, or more generally, we can use the area under the curve in the PV diagram. And sometimes there are some calculus methods that we can use. We can use integration to calculate that area if we know the form of the pressure as a function of volume. The other contributions in the first law of thermodynamics, we may be interested in the calculating the heat or the change in internal energy during a part of the cycle. And so the main formulas there would be that the change in internal energy is always related to the change in temperature by this formula NCV delta T. I'm going to explain today why there's a V here, why we call this the specific heat at constant volume. One thing that's very important is that this formula applies even if we're not at constant volume. So this formula delta U equals NCV delta T, it just works in general, even if we're talking about constant pressure or adiabatic processes. This is always the relation between the change in energy of the gas and the change in temperature. Okay, and then we have this relation that delta U is equal to Q minus W that I started with. And this is going to be often useful in actually calculating Q. Okay, so if we want to know how much heat enters the gas during a process, then often what we can do is calculate the change in U, calculate W, and then use the first law to understand what Q is going to be. So today we have a lot of questions where I'm basically just going to have you apply these ideas for various kinds of processes. Okay, so let's get started with this one. So this is a question to allow you to kind of understand what I was saying in the last statement about calculating Q using the first law. So have a look at this one and see what you come up with. Pause your video, and then we'll discuss. I will go get some more paper. All right. So hopefully you've had a chance to think about that. And so in this process, this is a good example where it's not really obvious, just kind of looking at the graph. It's hard for us to know how to think about Q. So what we really want to do is make use of our first law. And so the usual form is that delta U equals Q minus W. And so if we rearrange that, since we're interested in Q, then we can rearrange that to put Q on the left-hand side. And so now there's a couple of important things here. So the first one is that in our situation here, we have three different processes, but the initial and final states are the same in all three processes. And so what that's going to mean for us is that delta U is the same for all of them. We emphasized last time that delta U is a state variable. It doesn't depend on the process that you take. U is something that would be determined by the temperature and the pressure and the volume of your system. And so if I have the same starting point and the same ending point, then I know that the U at A is something which is the same in all cases. The U at B is something, it's the same in all cases. And so delta U is going to be the same. In terms of our formula, we have that delta U equals NCV delta T. And we can figure out the temperature using the ideal gas law once we know the pressure and the volume. Okay, so again, because the pressure and the volume change in the same way, the temperature changes in the same way. And so delta U is the same for all. Next, we can look at the work. And so basically, if delta U is the same for all of them, then the path that will have the largest Q is going to be the path that has the largest W. Okay, so the largest Q will be the one for the largest W. And that one is going to be, I think in the questions 1, 2, 3, and that's number 1, because that one has the largest area under the curve. Okay, so that's the logic. So the correct answer in this one is that the largest energy is for path 1, and the answer is A. Okay, so now we're going to start to, so that, these processes here were examples where we don't have any particular special description of the process. They're not constant volume or pressure or temperature. For the rest of the class, we're going to analyze processes that do have some special property that will come up often. And so it'll be useful to kind of understand what we can say about, say, constant volume processes or constant pressure processes, constant temperature processes. And so that's really the subject of the remaining questions in today's lecture. So here's one to get started on. It's asking about one process in this cycle, the process number 4, and you're asked to predict what the final temperature is. And this is going to be a very common type of thing that you'll have to do when you make these analyses. We'll want to know what the temperature is at all of the different points on the cycle, given some PV diagram. Okay, so take a minute to think about that. Pause your video, and then I will talk about it. Okay. So let me talk about this in a couple of different ways here. The first thing we notice about this process is that it's a constant volume process. Okay, so number 4 here, what we see is that the pressure is going up, but it's vertical, and so the volume is staying the same. And so one way of doing this is just to recognize that this is a problem that we've already seen in our course. It's like the constant volume gas thermometers that we were talking about, where we understood that pressure is proportional to temperature in that situation. And so we could actually very quickly do this question to say that the pressure increases by a factor of 2.5. And so the Kelvin temperature must increase by a factor of 2.5. 400 times 2.5 is 1,000. And so that would be a quick way of understanding that the answer is E in the situation, 1,000 Kelvin. Okay. But let me talk about a slightly more formal way to do this that works not just for constant volume processes, but for many processes, constant pressure, constant temperature, where we need to find some piece of information at the end of a process if we know information at the start of the process. So let's remember how we derive this proportionality between pressure and temperature. And I'll do it in terms of the ideal gas law, which we didn't really have early on when we were talking about this. So the ideal gas law says that PV equals nRT. For these kinds of processes that we're usually talking about in thermodynamic cycles, and the number of moles of gas is going to be a constant. My thing is not focusing very well today. Okay, so n is going to be a constant. And so that means that if I take the combination PV over T, that will also be a constant during our process. And so P1 V1 over T1 is always going to be equal to P2 V2 over T2. And this holds for any kind of process where the number of moles of gas is remaining constant. So any of our types of processes. In the specific process we have here, then we have that V is constant. And so what we could do is cancel off V from both sides of this equation. So V1 equals V2, And that means that P1 over T1 is equal to P2 over T2. Okay. And so then this is an equation that we can use, given the data in our question, to figure out the final answer. Okay, so this rearranges to P1 over P2 equals T1 over T2, and it's equivalent to just saying that pressure is proportional to temperature. Okay, so you can see that this will mean if I double temperature, I'm going to double pressure. So I'm emphasizing this because this method, it works. Even if volume is not constant, if pressure is constant, what you do is cancel off the pressure and you get V1 over T1 equals V2 over T2. If temperature is constant, you get P1 V1 equals P2 V2. So in many situations, if you're wanting to figure out the final values of pressure or volume or temperature after a process, that's the step that's the process that you'll take. Starting from the ideal gas law, we say PV over T is constant, and then you set whatever else is constant, you can cancel that out of the equation, and that'll be enough information to complete your question. Okay, so just to summarize, the answer was E there. Another one about process 4. Okay, so that's one aspect. We're wanting to predict what is the change in temperature, and then we're also interested in energy of various types, how those things change during the process. So have a moment to think about this question about what happens with Q and U and W in this process 4. Okay, so this one, it's really not too much that we have to do, except that realize we're talking about a constant volume process. And in a constant volume process, what we can say is that the work is always going to be 0. Okay, so the work is the pressure times the change in volume. If the change in volume is 0, then the work is going to be 0. So that's the main thing we need here. Once we have that, then we can look at our first law of thermodynamics and see that it reduces down to delta U is equal to Q. And so in this one, the answer is, B. Okay, so that's a good thing to remember. So summarizing all of the things we know now about constant volume, so what we could say is that for that kind of process, an example would be if you have a gas in a piston and the piston is locked in place, so you could heat it, the pressure might increase, but it would look like a vertical line on the PV diagram because the volume, which is measured on the x-axis, is remaining constant. And we understood that the ideal gas law tells you that either T2 over P2 equals T1 over P1, or equivalently T2 over T1 equals P2 over P1. So that will be very useful calculating, say, final temperature if you know how pressure changes and you know the initial temperature. In terms of energy, we learned that W is equal to 0 because there is no change in volume. And so the first law of thermodynamics simplifies to say that Q is equal to delta U. And then we always know that delta U equals NCV delta T. So the V on our specific heat at constant volume is basically, it's there because when you want to calculate Q for constant volume, then the formula is just NCV delta T. Okay, so the V sort of indicates that this expression works also to calculate Q at constant volume. Or if you were going to measure CV, then a way to do it would be to take your gas, put it at constant volume, add a certain amount of heat, and then see how much that changes the temperature. Okay. The jargon that we use for constant volume is isochoric. So you'll just have to remember a few different words for these processes where one of the thermodynamic quantities is remaining constant. So let's move on and contrast this with a different kind of process, where instead of constant volume, we could imagine that the piston is now free to move, but there's a fixed weight on top of the piston and a fixed outside pressure. Okay. So in this case, if I look at my system at any time, so let's say maybe before the heating or after the heating, if I look at my system at any time, then the pressure of the gas is going to be the same, because we're just balancing the force coming from the outside with the force coming from the inside. So let's have a look at this and assume that the piston is not moving. So maybe before we do the heating or after we do the heating, the piston settled down to some particular height. At that point, its acceleration is 0. And so the force up equals the force down. The force down, it's always the same. It's the outside pressure times the area plus mg of the weight. And so we could conclude that the inside force, which is the pressure of the gas times the area, is also always the same. It's equal to that constant outside force. Okay. So that's why this kind of a process, when you see a moving piston with a fixed weight on the top, that's a way to achieve a constant pressure process. And in this question, I'm asking you, if we heat the gas in this situation with constant pressure, and we want to compare how much heat do we have to expend to do that, is this going to be greater than the amount of heat we needed at constant volume, or less, or the same? Okay, so take a moment to think about that, and then we'll talk about it. Okay, so let's have a look. And in this case, there's an intuitive explanation of the answer, and there's one using our equation. So let's start with our equation. Let's start with our first law of thermodynamics, which is, again, delta U equals Q minus W. And we're interested in Q, and so I will rearrange this again to say that Q equals delta U plus W. And so using this equation, what we can realize is that delta U is going to be the same in both cases because it's just related to the change in temperature. Okay, so delta U is always calculated by this formula, NCV delta T, regardless of if it's constant pressure, constant volume. This is our formula for delta U. And in this question, we're told that the change in temperature is the same in both cases. So delta U is the same in both cases. And to figure out which Q is larger, all we need to do is figure out which W is larger. So it's a little bit like our first clicker question. W equals 0 for constant volume, and W is going to be greater than 0 for our expanding situation. Okay, so W is greater than 0 in the second case, and so that means that Q is larger. So our conclusion is that Q is larger for constant pressure. And so our answer is, our answer in this case is C. Okay, but let's intuitively understand this. Okay, so that was with the equations. What is this really telling us? Why do I need more heat in the second case? Well, it's kind of obvious when you look at the pictures. So what is our heat doing? Our heat is either going into heating up the gas itself, to increasing the temperature of the gas. But in the second case, some of our heat is clearly going into lifting, it's being converted into mechanical energy, and it's lifting up our weight. Okay, so in the first case, all we had to do was increase the temperature of the gas. In the second case, we have to increase the temperature of the gas and lift the weight. And so we're going to need more energy in the second case. We're going to need to add more heat in the second case to do both of those things. So it's going to be useful for us later to actually figure out how much more heat we need in order to heat the gas at constant pressure. And so let's actually do this calculation in detail to figure out specifically, like, what is the ratio between how much heat we need in the constant volume case and how much heat we need in the constant pressure case. So we'll start with our first law and write that the change in U is NCV delta T. And now, because it's constant pressure, we can say that the work is just P delta V. So that's the case. Constant pressure is the case where we can use this simple formula. What we're going to do is now rewrite the second term in terms of the change in temperature. Okay, so our ideal gas law says that PV equals nRT. And now if we have constant pressure, then the only things in this equation that would change in our process would be the volume and the temperature. And so the ideal gas law for constant pressure says that P delta V is going to be equal to NR delta T. Okay, so that assumes that the pressure is not changing here. So now we could rewrite the second term here in terms of the change in temperature. So I get Q equals NCV delta T, and then plus, now I'm replacing P delta V with NR delta T. So plus NR delta T. And now we can combine the terms to see that the Q for a constant pressure is N times CV plus R times delta T. Okay, so that's what's showing on this slide. And once you have that, it's actually convenient then to make a definition, which is to say that CV plus R, this constant appearing in the formula for Q, we'll define that to be, hello, focus, we'll define that to be CP. Okay, so this is just a convenient definition because this combination of things appears in the formula for Q at constant pressure. Then you just give it a name, CP equals CV plus R. And so once you have that, then we can write the formula for Q at constant pressure as N times CP times delta T. Okay, so this is the specific heat at constant pressure. So kind of to summarize, if you wanted to calculate delta U at constant pressure, you would still use NCV delta T. If you wanted to calculate Q at constant pressure, that's when you use the C at constant pressure. Okay, and so if you wanted to, you could measure CP in an experiment like the one we've shown here on the bottom. So I could see how much heat I need to add in order to increase the temperature a certain amount at this constant pressure, and then taking the ratio of Q and N delta T, that would give you CP. Let's summarize all the things we've understood for the constant pressure process now. Okay, so we understood what constant pressure processes look like. They have some fixed external force. You might still have an expansion of your gas, but because of this fixed external force, the pressure is remaining constant during the process. And so it looks like this. Horizontal line to the right if we're talking about expansion, or to the left if we're talking about contraction. In this case, the ideal gas law is going to give you that. So we have PV over T is constant, but P is constant. So V over T is constant. We can rearrange that to say that T2 over T1 is V2 over V1. So in this case, the pressure is constant. If you see that the gas expands, then the explanation is that it's because the temperature is increased and it's proportional. Okay, so T is proportional to V for a constant volume process. In terms of the energy, we understood that we can use the simple formula to calculate work. It's just P delta V. And then we've now understood that in order to calculate heat, using the first law, we learned that the combination of delta U plus W ends up giving you this formula, NCP delta T. The jargon we use for constant pressure processes is isobaric, and I like to remember that the instrument used to measure pressure is a barometer. And so that's where this baric comes from. Isobaric is the constant pressure. All right. So moving along here, let's talk about our next kind of process, which is a constant temperature process. So how do you keep the temperature of a gas constant during some process where it might be expanding or contracting? The way to do it is have your gas in contact with what we call a heat reservoir. So that's just some liquid or solid that's at a temperature T that you're keeping fixed. And then what happens is that if you expand or contract the gas very slowly, it will remain in thermal equilibrium with the surroundings. And so, for example, if you tried to compress it and it heated up a little bit because you added a little bit of energy with your mechanical work, then if you're doing it very slowly, that extra energy can now leak into the heat reservoir. So as long as you're doing things slowly, you should remain in thermal equilibrium. And so that would be the picture of a constant temperature process. Okay, so take a moment to think about what it means in terms of the energies appearing in our first law of thermodynamics if we know that the temperature is constant. Okay, so let's have a look. And in one way of thinking about this is very simple, but it's a little bit counterintuitive in another way of thinking about it. So let's be clear on exactly what is it that's equal to zero, and in this case. Okay, so you might say maybe they're both equal to zero, but let's kind of break it down and come up with an argument. So the thing that we know for sure, if you have constant temperature, is that delta U must be zero, because delta U is completely determined by the change in temperature in all situations, and the change in temperature being zero therefore means that delta U is equal to zero. What about Q? So Q, again, is something that it's hard sometimes for us to understand. Is in this process, is there heat going into the gas or out of the gas, or is there no heat being transferred? But I would always recommend thinking about what the first law of thermodynamics tells you in a situation where you're not sure about what's happening with Q. So in this case, the first law of thermodynamics, when delta U is equal to zero, it's going to say that Q is equal to W. Okay. And then we can understand what's going on in this case. So because Q equals W, and because the gas is expanding, W is positive, and so Q is going to be positive. Okay, so the answer in this case, delta U is zero, but Q is positive. Okay, and the way to understand it physically is that if I pull up on this piston, so if I allow the gas to expand and then the gas is doing work, if we didn't allow any heat transfer, then the gas would actually cool down. Okay, so we'll talk about that process, the adiabatic processes later on, where we don't allow any heat transfer. So naturally, the gas would want to cool down when it does work. But in this case, it's in contact with our thermal reservoir. And so heat is going to flow in from the heat reservoir in order to keep the temperature constant. And so that's why we have a positive Q. So what does it constant temperature process look like on the PV diagram? Okay, so take a minute to think about this one, and then we will discuss. Okay, so the constant temperature processes are a little bit more complicated looking, but we can understand them. Oh, let's start with a regular version of the ideal gas law. Okay. So PV equals nRT. Okay, there we go. PV equals nRT is our ideal gas law. In this case, we have a constant temperature. And so what we could say is that PV equals constant, or P is equal to nRT divided by the volume. Okay, and so what does that mean for our graph? Okay. So if PV is constant, that means if V increases, then P has to decrease. Okay, so the answer here is either B or C. But specifically, if I think of P as a function of V, which is my x-axis, then we see that it's like a 1 over x function. So P equals nRT divided by V. The top thing is a constant. And so it's like the y equals 1 over x or 2 over x or 5 over x function. It's a function that asymptotes to the x-axis and it asymptotes to the y-axis. So that's answer C here. You know, in order to decrease the pressure to 0, I would have to take V to infinity. Whereas in answer B, it looks like the pressure is going to 0 at some constant volume V. So this is something that you'll learn to recognize. When you have a constant temperature process, it looks like a curvy decreasing line, and it's a very specific shape. Okay, so we're actually going to see that the adiabatic processes also look like curvy decreasing lines, but this one in particular is exactly like a 1 over x function. Okay, so summarizing so far, what we've learned is that constant temperature processes, they look like they have PV equals constant, or we could say that P1 V1 equals P2 V2 if we wanted to calculate the final pressure or volume. The relation between pressure and volume is that pressure is inversely proportional to volume then. And on a graph, that looks like this decreasing graph with a positive second derivative. Okay, so it's curving, it's concave up. What can we say about the energy in constant temperature processes? We've learned that delta U equals 0 because there's no change in temperature. And so our first law says that Q is equal to W. But now, what if we actually want to calculate Q or W for these constant temperature processes? So that requires our more complicated method of finding the area under the curve, because in this case, pressure is not remaining constant. Okay, and so this is kind of one place in the course where we really do need a little bit of calculus. We need to apply the method that I talked about in last class. And this is something that you're going to be, well, probably have already done in tutorial this week. So let me just review that for you. And really, we're only going to need to do this once. We'll see what the final answer is, and then that will be the thing that you'll actually apply when you need to analyze constant temperature processes. But let's go through this once, just remembering what the mathematical recipe for calculating this area is. And so our first step is just to understand what function we're talking about. And so we've already done that. We've understood that P as a function of V is equal to this constant nRT divided by the volume. The second step in our recipe was to find a function whose derivative was equal to this function. So to find an antiderivative of this function, constant over v. And hopefully by this point in your calculus courses, you've learned that the antiderivative, or that, if you start with the logarithm function, the natural log, and you take the derivative, you get 1 over volume. And so you could check that this function, f of v equals nRT log v, natural log of v. If you take the derivative of that, then it gives you this function p of v. Once we have this antiderivative, then the area is simply the difference between our antiderivative evaluated at the final volume and the antiderivative evaluated at the initial volume. So plugging those things in, we get nRT log of final volume minus nRT log of initial volume. And the result is, using the logarithm identities, that log of b minus log of a is log of b over a, we get this final equation. W equals nRT log of v final minus, divided by v initial. Okay, so now we can complete our summary for constant temperature with this formula that if you want to calculate the heat, it's equal to the work, since delta U equals 0. And then the work is equal to the area under the curve, which we have now once and for all time calculated to be nRT, which is our constant temperature, times the number of moles times the ideal gas constant. Then you multiply that by the logarithm, this natural log, the log of the base e, of the final volume over the initial volume. So you will never, again, have to do that integration because this is always then the formula when we have constant temperature. And in terms of the words that we use for constant temperature processes, isothermal, that one's the easiest to remember. So today we've seen constant volume, isochoric, constant pressure, isobaric, and constant temperature, isothermal. And next time we're going to talk about one more kind of process that's important, which is adiabatic. And that's a process where Q is equal to 0. And so we'll see that on Monday. Have a good weekend.